So up until now, we've kind of been ignoring that rest energy term. And that's because in most cases, the rest energy is the same on both sides of the energy conservation equation. So you have E rest initial plus K initial plus work is equal to K final plus E rest final. Now, part of the problem is when we're dealing with low speed situation, E rest tends to be several orders of magnitude larger than these. And so if you go ahead and try plugging things into your calculator, all you're really going to see is the rest energy terms. So up until now, we've kind of been subtracting this from both sides, realizing that they're equal to one another, and subtracting these from both sides. But when the rest energies are different, we do need to include these. And typically the rest energies come into play whenever there's a change in identity of the particle. So let's say that we have a neutron, which is a neutral particle at the nucleus of an atom. So this is our before picture. And then afterwards, we have a proton and an electron moving off in different directions. The neutron can in fact decay into the proton and the electron. The important thing here is that the charge is still conserved. We started off with a neutral charge here. The proton has a +1 charge, the electron has a -1 charge, and so we still have a neutrally charged system. But by splitting up, there actually is a change. If you were to add the mass of the proton plus the mass of the electron, you would get something slightly different than the mass of the neutron. And that change in energy is coming about because of that change in energy. These two things were actually, you could think of them as being bound together inside the nucleus. And binding energy has mass associated with it. We'll see that in a later section in the chapter again. But whenever you do see changes in identity, you're going to have to include the rest energy in the term. The other thing to pay attention to in this chapter is the definition of the electron volt. This is another common type of unit used for energy. And the electron volt comes about, it's the energy associated with an electron moving through a potential difference of 1 volt. Now, we really haven't talked about that too much in this course. You'll get to that more in the second half in 282. But for now, it just suffices to say that it is a type of energy that's related to the joule in this fashion. And it's very handy when we're dealing with things like atomic energies, because the atomic energies tend to be on the order of a few eV. And so rather than having to write some number with a really big or small exponent on it, we can write things that are close to unity, which just makes writing things a little bit easier.